Have you ever wondered why chemists are so good at solving problems? It's because they got all the solutions. What? I told a chemistry joke and there was no reaction? Well, how about this one? What is a chemist's favorite plant? A stoichiometry! oh. Oh, come on. That was funny. Hello, everyone, and welcome to Scientific Theory, where you better get used to my bad jokes because I'll be making them periodically. Get it? Because, like, the periodic table? Anyways, moving on. Did you know that the visible universe is estimated to contain 10 to the 78th to 10 to the 80th atoms? That's 10 followed by 80 zeros. And every one of those atoms is made up of something. There are an incredibly large amount of substances in the universe, and all of them are composed of molecules, atoms, and elements. Well, what's the difference, you might ask? Let me use an analogy. You walk into an ice cream store and they have 30 different flavors. You have vanilla, strawberry, rocky road, and many more. Each of those flavors are an element, something you will build your dessert from. The smallest amount of ice cream the store will sell you is a scoop, and that's an atom. If you want, you can put 2 or more scoops of ice cream together, and this is a molecule. I'm here to explain how our full dessert, or molecules, are made. To do that, however, we first have to understand the flavors, or the elements. To do this, we simply look at a helpful tool called the periodic table of elements. This table is composed of all 118 currently known elements, and I say currently known because scientists have discovered new elements within the past 5 years. Although there's a lot of information contained on this table, we only have to know 2 things. The first is how to identify an ionic or covalent substance, as this will come in handy later. It's really simple. An ionic compound is a substance made up of at least 1 metal atom and 1 nonmetal atom, while a covalent substance is purely nonmetals. How do we figure out which elements are metal and which are not? All you need to do is look at this line on the table. Anything to the left of it is metal, and anything to the right is a nonmetal. Using the ice cream analogy, if we had an ice cream cone with a scoop of Na and a scoop of Cl, we'd have an ionic ice cream cone. If we only had 2 scoops of O, though, it'd be covalent ice cream. The second important thing is how to identify valence electrons, which I'll explain in more depth later. Simply put, you look at the number above an element's column, and that's how many valence electrons we have. But what are valence electrons, you may ask? If we look at the model of an atom, we see it's made of a nucleus, the blob in the center, which is made of positively charged protons and neutrally charged neutrons, with negatively charged electrons orbiting the nucleus. Am I sure? I'm positive, and so are the protons. No? Still nothing? Okay then, let's move on before I bore you. Oh! Nice segue, because in the Bohr BOHR model of an atom, there are different orbitals around the nucleus, and the outermost ring is the one that contains valence electrons. Now that we know how many valence electrons are in any given atom, we can finally start moving on to molecular structure. Oh yeah! Since it's too complicated to draw entire atoms for the molecular structure, scientists usually use Lewis structures to draw the molecules. It's a drawing with the abbreviation of the atom in the middle with little dots around the outside representing the valence electrons. To make a Lewis structure, we have to join the valence electrons in such a way that each atom has 8 dots around its abbreviation. Now, here's the catch. Remember the ionic and covalent compounds I talked about earlier? Those come into play now. If a substance is ionic, the atoms can only give electrons to other atoms, or take them away. You know why? Because their name is bond. Ionic bond. Taken, not shared. No? Still nothing? You people must have no sense of humor, because that joke was hilarious. In reality, though, it's because all atoms want to obtain 8 total electrons. If you only have 1 electron on the outside, though, and 8 in a ring below it, is it quicker to get another 7 or just give away the 1? That's why ionic compounds bond that way. If we use NaCl or table salt, we get a good example of this principle. See? The sodium, or Na, gives us 1 excess valence electron to the Cl, giving both of them the full 8 valence electron ring. And, unlike our badly behaved ionic atoms, for our covalent atoms, sharing is caring. Since covalent atoms tend to have a higher number of electrons, it's easier for them to share electrons to complete their outer ring, rather than giving or taking. We still use dots for unshared electrons, but for shared electrons, we draw a line in between the atoms, which represents the 2 electrons linking together. Of course, this only shows molecules in 2 dimensions, but what about in 3 dimensions? Well, depending on how many unpaired valence electrons there are, as well as how many atoms there are, the shape will change. For a molecule with 2 bonds, it will either be linear with no unbonded pairs, or bent with 2 unbonded pairs. For a molecule with 3 bonds, it will either be trigonal with no unbonded pairs, or pyramidal with 1 unbonded pair. And lastly, if it has 4 bonds, it will be tetrahedral. The difference in shape is because the extra negatively charged electrons push as far as possible in the opposite direction of any positively charged protons in the molecule. Because of this, you can have different shapes with the same amount of bonded atoms. Well, hey, that's just about it. Looking back, the stuff you learned really had a lot of substance, didn't it? Man, with all these chemistry puns, I have been in my element. Alright, I can hear you sighing. I'll stop. I was planning to leave you with another awful chemistry joke, but it looks like all the good ones are gone. But hey, that's just a theory. A scientific theory. Thanks for watching.